Thanks. Okay, today we have Julien Codsi, I hope I've not butchered that name, um, who was a master's student in Oxford and is going to be talking about the work that he did on stabilizer decompositions of quantum circuits for the purpose of simulation. Take it away.
All right. So hi, everyone. As I said, my name is Julien Codsi. I'm a PhD student in the University of Montreal. And today I'm going to talk about stabilizer decomposition and some, I guess, new, recent development into that field. So the main ideas behind this work they come from my master thesis. They're based on, I guess, 3 papers, 2 from Alex, John, and Renaud Villemar on how to use stabilizer decomposition within the ZX calculus, but also some papers from Bravey, Brownie, Kalpin, Kempel, Gossett, and Howard on the stabilizer rank decomposition. There was the first paper on the subject. So I guess before going into stabilizer decomposition too much, I'll go quickly through a classical simulation of quantum circuit. It's within the Clifford fragment, because I'll use some property of the algorithm we have for this later on. So, okay, today I'm going to talk about strong simulation of circuits. So what I mean by strong simulation is if I have a circuit and I have an input and an output, I want to fix the input to, let's say 0 to the n, and fix the output to whatever I want, but without loss of generality. You can most of the time takes 0 to the n again. I want to know, it's not, that's a cat, that's a bra, yeah. Anyway, we want to know what's the amplitude of the state, and so we can know the probability of having that output. That contrasts with the weak simulation of a quantum circuit, which is I just set the input and I want to see I would just want to sample the output probability. You can do also those kind of simulation with those kind of techniques I'm going to talk about today, but today I'm mostly going to focus on the strong simulation because it has a really clear ZX interpretation. It's just that you take your circuit, you plug in the output and the input, and you just have to do a contraction of the tensor network, because your ZX diagram has no input, no output. It's just a complex number. You just want to compute it. Okay, so within the Clifford fragment, what it looks like is you have multiple of pi/2 on all of your spiders, and you want to be able to, so you have a whole diagram like this, and you want to be able to find the value of that diagram, and the algorithm goes, it's going to be a really brief intro. If you've the first time you've seen this, maybe it's going to be a bit too quick, but if not, I guess it's a good refresher. So the first step of the algorithm is to make the diagram graph-like. Graph-like, and what I mean by graph-like is you take everything and you make it green, and afterwards you cancel all the Hadamards you can, and you do the most spider fusion. So at the end of the day, you only have green spiders and Hadamard edges. And then once this is done, you use 2 operations. One is called local complementation, that looks like this. This is my first time using this kind of hybrid, preparing pictures and also just dropping them in the board. So I hope it's not too janky, but kind of like it. So you can do local complementation, which is an operation that removes anything that has a pi/2 phase on it. So if you see this node just disappeared, this spider is just not there anymore. So you can do this all the way down until you don't have any pi/2. And then you have pivoting, and pivoting is another operation, which is this one, which gives you that you can remove any 2 spider that has a pi, multiple of pi on it. So those 2 spider are just straight up gone from here, I guess. Yeah. And in the Clifford case, this is enough to prove that everything, you can simplify everything, because since once you have nothing with a pi over 2 on it, everything either has a pi or a 0 because you're in the Clifford fragment. And then the pivoting will remove everything else. And then you're left with a number, and you just proven Godin-Menil theorem in a very diagrammatic way. Okay. Well, this is cool, but this is not all, because like otherwise quantum would like have no, just a polynomial advantage over classical things. Like the bigger, like the bigger fragment that we'll consider here is the Clifford plus T fragment, which is the same, but with multiple of pi over 4. This is approximately universal. And so you can represent pretty much everything with it. But the like the algorithm we just showed, it kind of works on this on a ZX diagram with pi over 4 on it. It kind of works, but not all the time. What I mean by this is that those two rules can still apply, and they'll kill everything that has a pi over 2 on it, and everything that has like two things that are connected that have a multiple of pi. But where it breaks down is that that does not cancel anything. Basically, at the end, what you end up by doing this procedure is kind of a simplified form where you have a bunch of, I'll just put T to say like an odd multiple of pi over 4, whatever it is. And those can be connected however we want. And you'll have some Clifford things, which will be just a multiple of pi, so like k pi, and like k1 pi, k2 pi. And those cannot be connected together because otherwise there'll be a pivot, and those will be connected to some of the T gates. And the fact that they cannot be connected together will be somewhat important in a minute. Okay, so not all hope is lost when you arrive at that state, because now you can do what we call stabilizer decomposition. And I'll briefly go through the idea of stabilizer decomposition outside of the ZX world. So outside of the ZX world, the idea of stabilizer decomposition will look like you take any state that is probably a result of a quantum circuit, and you want to express it as a linear combination of I equal 1 to k of alpha I, phi I, where phi I is a Clifford state, meaning that it's a result of a Clifford circuit. Let's just put Cliff. So why is that a good idea to do something like this? Well, if you want to project that state onto another state, I don't know, A, well, you can, by linearity, this just falls here. And all of those are Clifford, so this is polytime. So projecting into like on a state and do a strong simulation, just take time that is big O of k times poly of n. So this is good. If k is small, this is really good. This k is large, then but this will work pretty well when you have like something like low T gates or low non-Clifford things in your diagram. And so the idea is to try to minimize the k on this sum. For a given state, the minimal k is what we call the stabilizer rank of that state. And it's like we strongly expect that stabilizer rank in general will take exponentially many terms, because again, otherwise you won't have any advantage over on quantum over classical. So okay, so that's the idea. Like the non-ZX version of this idea. The ZX version is kind of nice, like a really visual intuition to it. Is basically when you have whenever you have like a pi over 4, like a T gate, you can just decompose it by almost by definition in a red spider plus e to the I pi over 4 times the red spider with a pi. So if you do this on a diagram, then you end up with two diagrams, but each of the diagram has one less T gate. And then you can repeat this for all of the T gates, and that give you a bunch of diagrams that are purely Clifford, and the whole pivoting and everything will work, and you will be able to simulate that way. Doing this gives you an algorithm that is big O of, will forget about the polynomial factor, but 2 to the t, where t is the number of t-gates. And you can actually do better than this. For example, you can do round of simplification of like ZX simplification in between every time you replace a t-gate by the two terms here. That works nicely because like there will be some pi copy happening all around with those things, so that helps a lot. But also you can do better if you start to look around a bit and you realize that like you have some decomposition that are more efficient for t-gates than this. For example, you can do something like this. So you can take two t-gates and transform it into two Clifford state. So doing so, you get something where your algorithm is big O of 2 to the alpha t, where alpha is 0.5. And the reason I put it with an alpha is because like in a second it will be there's even better to do, and it's a bit more intricate afterward. So then you can play a bit more around it, and then people have found this decomposition. Okay, so most of these decomposition, just to mention, like people just don't try them like at random at hand until they find something. I mean, I say that I've seen Vilmar do it a bit, but anyway, I've done it myself, but anyway. So those decomposition are mostly found through simulated annealing over the space of Clifford state. There's a really clever algorithm for it that it did not implement, but I did use a lot. So those, okay, so you can find those kind of decomposition where here you take 5 t-gates and you transform it into 3 terms in which all of them have 1 t-gate left. So this you can see it as a 4 t-gates into 3 terms, which give you the same 2 to the alpha t, but here alpha is approximately equal to 0.396. I think it's log 3 over 2 or something like that. The log base 2 of 3 over 2, if I remember correctly, something like that. Or over 4, actually. Yeah, over 4. Yeah. So this is like a, kind of was the state of the art on those kind of things. And that works really nicely and it's a lot more efficient. We save more than like a square root of the time taking by just taking the trivial stabilizer decomposition, which is this one. But there are even better things to do. So here we see that like we always started to decompose a state that looks like a t-gates tensored n. And that works. And that is fully general because whenever you have a ZX diagram where you have a bunch of spiders with some of them having t-gates, then you can always just like fuse out the t's. So like, for example, I can just take that away, put it here, and do the same for a spider. And then this is the t to the n that I was looking for. So like you can always apply this decomposition, and we have kind of a good way to do it. However, for some state that have a bit more structure, we have better decomposition than this. So there's one category of state that we call a cat state. So cat state, which looks like, is it like cat n is equal up to a number because like there's some power of 2 going on here. Like this, pi over 4, pi over 4. And you have a bunch of them, n of them, and that's what we call the cat n. And this has better, in not all the time, but most of the time, this has better decomposition than just t to the n. I mean, for example, if we take cat 3, which looks like this with a pi over 4, and like this, pi over 4, and like this, pi over 4. Then if we use the trivial decomposition on, let's say, that spider, what it gives us is 2 terms. And I guess I can probably just copy paste, I guess. So you can get this. Oh, it's kind of fancy. And then I can paste it. This will be equal to this, but now you remove that spider and you place it up to a number. It will be equal to like this, and then this will be a red spider plus the same thing. I guess I can do this again. Oops. Yeah. And paste it. And the same thing, but here you have a pi, and there's a multiplicative constant here. Let's see. And in both of those cases, what will happen is after color change and fusion, I'll do it in the first term so we can see. After color change and fusion, this just disappears. And this is just the identity. And this disappeared also. And then the two Hadamard cancels. So you have a single wire here. And those two T-gates fuse. And when two T-gates fuse, the cool thing is that they kind of jump from the Clifford plus T fragment to the Clifford fragment because they become a multiple of pi over 2. And so this will become something that is fully Clifford, just being a pi over 2. Okay. And the other thing happened, the same thing happened on the other term. So effectively, we remove 3 T-gates for two terms, which is better than terms, which is better because this is like an alpha of 0.3 periodic. So those kind of states are nice because they have really like neat decomposition, but they're not as general. And I mean, and so you kind of, what you can do is you just take your ZX diagram, you look for cat state. Whenever you find some, you look for the decomposition. If it's good, you do it. If not, if you don't find any cat state, you just go back to like the magic state injection of like a t to the n, and you decompose it. Okay, so that's all of this already pre-existed before people already found this before I started working on those kind of problems. One thing I realized that was kind of interesting. It's not that like, it's just kind of curious. Like, it's really similar, but like somehow it works kind of nicely. If we introduce another family of state, which is called the star state, I mean, I called it that. I don't know if that has a real name, which is equal up to a number to the same thing as a cat state, but with a pi root 4 in the center. So it's kind of the same as a cat, but almost like just this little added thing. And it's defined in the same way where there's n of those. Then those also have good decomposition, like better than what we'd expect from just decomposing the T gates. And but like those states, they have the same kind of drawbacks as star states. Is like you're not guaranteed that you can find those states all the way down by using those decomposition again and again. So it's like having good decomposition of star state doesn't give you like a better alpha for the general algorithm. Same thing for cat state. But the interesting thing is that if you have good decomposition for both, you get a good decomposition in the general case. So there's a kind of a lemma that is kind of neat. Lemma. In a Clifford, like in a Clifford plus T diagram. Oh, just diagram. I guess it should put simplified here. Simplified. Either there exists a cat, there exists a star, there exists a star, or it is just a number. So in some sense, the cats and the stars are kind of dual. Like if one doesn't exist, the other one needs to exist, and that in itself is enough to prove that like if you have good decomposition for stars and cats, then you have good decomposition in general. And the reason why this is true, kind of proof. I guess I'll go back to the drawing. It's kind of the reason I did the proof of the Godesman-Neal theorem at the beginning, because it kind of relied on this. So what happened is, like either you have a Clifford thing in your diagram. If you have something that is Clifford, it will be either a 0 or a pi. And you can, if there's a pi, you can just push it through. So you can always assume that you have a 0. And that 0 cannot be connected to anything Clifford because otherwise some pivoting will happen. So it needs to only be connected to T-gates, meaning that if you have a Clifford, it's a cat. So the only way you don't have a cat in your diagram is that you have nothing that is Clifford. If you have nothing that is Clifford, it means that your diagram is fully just made of T-gates. So any T-gates, if you look at its neighborhood, it's also a bunch of T-gates. So it's a star state. So you always have either a star state or a cat state. And which makes it nice because it gives you a path to prove good decomposition without ever having to really rely on like the decomposition of T-gates in general. Okay, so that's kind of a neat thing. The sad part, I guess, with those kind of things is that we don't have good decomposition necessarily all the way down for those kind of state. I'll can copy paste some decomposition that exists. So for example, I won't go through all the details. Like I had okay, you can investigate to improve the alpha we found. We did investigate something like cat n to the k. And so those have even better decomposition and the whole argument works. But if you look like here for star state, you have decomposition. They all have like slightly better alpha than 396. Like here you have some really good one. But in general, we tend to have some decomposition that goes to that 396 that we talked about earlier. I mean, I can, for example, all the cat state decomposition, if you look at how they go, they start really good and they kind of converge to that 396, and the same happened for the star state. So for the star state, it looks like this, and it also converged quite quickly. It converged okayly fast to 396. So as of now, we don't have an argument for better alpha than 396, but in practice, we can always use those better decomposition, and if we have small cats and stars, then it works a lot better than not considering those. And it gives you sometimes some silly things, like if you have what is 6 cat 37, 6 stars 37, you can decompose it in 5.815 to the 10 times 10 to the 26 terms, which is slightly better in 396, but still a lot of terms. So you can play around with those kind of ideas, and they kind of fun to work with. And also those kind of algorithm, kind of interesting to mention, they take like little to no memory, because you can always do this decomposition kind of in a depth first search way. So you can always go down until you find a number, and then you go back. So you don't really have to consider a bunch of diagram at the same time. At most, quadratic, I think the amount of memory you need is, I'm not sure for linear, but for sure it fits into quadratic amount of memory within the size of your diagram. So to have like really neat things you can do with this. And it's also super easy to parallelize, because if you have a sum of two terms, you can just like throw like the first term on the thread and throw the other term on the second thread, and then you just add the number at the end, and the both thread don't really have to talk with each other at all. So it has like really neat properties. Okay. Now, so that was for decomposition of kind of specific states. And now I'm going to talk about like kind of jump to another kind of aspect to stabilizer decompositions. I'll go to something that I call graph cuts. Graph cuts. Okay. So that idea is kind of simple. It's whenever you're doing this like decompose and simplify procedure, if at some point you end up with a diagram that looks like this, where you have like D1, like two subdiagrams T1 and T2 that are fully disconnected. And let's say for the sake of the argument that each of those two diagrams has half of the T gates, then normally you would do the normal algorithm of stabilizer decomposition, which gives you a big O of like 2T alpha T if you neglect polynomial factors. But if you think a bit more about this, like this is a complex number, this is a complex number, we can just multiply those two complex numbers at the end, and we don't really have to consider like the whole diagram all the way down. So you can actually, by doing this kind of divide and conquer step, you can get away with 2 to the alpha T over 2 times 2 because you have to do it twice. So, which is really neat. But like theory, this doesn't really happen all that often, because otherwise, like if you could do like divided by 2 all the time, you'd get like something that is polytime. So this rarely happens. However, like if you have something that looks a lot like this, but it's not exactly like this. For example, if you have an edge here, then you could say that, oh, the whole argument just doesn't work anymore because it's not multiplication of two complex number. But actually, it's kind of still is, because you can take that edge and cut it. And by cutting it, I mean you take the edge, and by the resolution of the identity, this is just this plus pi. I didn't put the color on my spider because it's true for both colors. So, okay, so you can, for the cost of 2 terms, you can cut it in 2 and still get the same kind of reasoning happening. So you can kind of look for those, and more generally, you can cut, like if you have to do a cut of size C, then you can get away with making this times 2 to the C. And whenever you have some like places in your diagram that it gets like kind of sparse and it's like connected but not that strongly connected, you can kind of abuse this like weak connection in your diagram to make it happen, and like to cut it there and have 2 diagrams. And but okay, it's kind of cool because it's kind of relates to a bunch of known graph theoretic problems. For example, there are good algorithms for what they call the balance cut problem. And the same goes for the sparsest cut problem. Which are 2 problems that are kind of related, that like do this balance thingy where like they need to have to cut the graph in half, and they want to minimize the size of the cut. But like, I guess sparsest cut, they allow some imbalance parameter, while balance cut like is more like, oh, I have those many, like that many edge to cut, like how balanced can I make a cut on my graph? So it's kind of the two sides of the same coin. And you can use those algorithms to find good cuts in your diagrams, and it works pretty nicely. And okay, even though those algorithms, they're like not, I think those problems have been shown to be like NP hard or something, but they have like really good heuristic, and we only really care about the heuristic because we're like proving something here. We're just like using those algorithms to find good cuts and make it happen. Then you can use those algorithms to find good cuts and make it do this step of divide and conquer in your diagram. But actually, you can do like better than this. The reason is, like, whenever you have an edge, your diagram like this, whatever the angles are, you can always see it as like a tiny bit of real, like you can put the Hadamard box back in, and you can, instead of cutting that edge, as we talked about earlier, what you can do is just take that spider here and express it as, oops, not like this. So instead of using a resolution of identity, you use the definition, like you use the fact that you can cut like a whole spider at a time for 2 terms. So instead of considering some edge cuts in your graph, you can actually consider vertex cut. And those are always more efficient because instead of considering cutting an edge, you can just cut one of the vertex at the end of the edge. So we can get away by using those problems, but the vertex version, which are a lot, like in general, a lot better, and at worse, as bad as the other one. Vertex cut, vertex cut, vertex cut. Okay, so those kind of techniques work really well when your diagram is somewhat sparse, but that's like not always the case. But when you have it, it works really nicely. You can show with those kind of ideas that, like, if you have like for example, a nearest neighbor circuit, you can always do a simulation. If it's sub-quadratic in depth, then you can always do it in. You can always do the simulation in sub-exponential time, because you can, for those kind of circuit, you can use the fact that like your diagram needs to be planar, and you have kind of good like a theorem about existence of good cuts on planar graphs, and you can always kind of use those kind of ideas, which are really cool. So you have this, and okay, so that's one thing I've been doing last summer, and one thing I've been working on since is kind of improving upon those ideas. It's something that called subgraph complement cut, or I mean cut, we'll put in parentheses. Okay, so in addition to being able to cut an edge and cut a vertex, what you can do is a kind of a related operation, which is, I'll show it. I'll plug my diagram here. Okay, I'll go through step at a time. So, okay, a subgraph complement is a graph operation where you take any subgraph of your graph and you do the complementation of that subgraph. Or if you like to think about things being added mod 2, it's kind of adding a complete subgraph of your graph mod 2. So with the edge, like if they were there, they just kind of pop out. And if there was no edge, now there's an edge. And you can do this operation in the ZX diagram for the cost of 2 terms. So for the same cost of being able to cut an edge or cut a vertex, you can do the subgraph complementation operation. And the reason why is this little proof here. So if you have a diagram and you have S being your subdiagram you want to cut, what you can do is do this trick where you add a pi over 2, but you add a red spider. So adding the red spider, because of pi copy, this copies through, and like it's like this just copies through, change color, and like basically you haven't done anything, right? So this is true, but here, once you're here, you can do the resolution of the identity on that wire to, I did the green resolution of the identity. So that's exactly what I did here. And after that, up to a number here, I think I'm missing a constant here, but whatever. You get this, and after spider fusion, you get the sum of those 2 terms. And those 2 terms, what's nice about them is it's a pi over 2 connected to a bunch of stuff. And if we recall, pi over 2 connected to a bunch of stuff is exactly the situation where you can apply local complementation. And local complementation does exactly that. It adds a complete subgraph mod 2 normally it's the neighborhood of this, and in our case we make the neighborhood being any arbitrary subgraph of a graph. So we can always perform where was I? Yeah, here. So we can always perform this, and I guess this is but it's still the constant, and there's like the angles are slightly different in both terms. But the idea is the same. You get like the graph is the graph just changed by a local complementation, a subgraph complement. And okay, the reason why this operation is interesting, there's two reasons why. First, I'll go like somehow like another lemma. Subgraph complement cuts, I guess, subgraph complement that. Subgraph complement cuts are always better than vertex cut. Better or equal. And so in the same way that we improve upon edge cut by considering vertex cut, you can always improve by not considering vertex cut, but actually considering subgraph complement. And the proof of this is kind of simple. If you want to do the cut, a vertex cut, it means that you want to cut your graph into pi1 and pi2, and you have like the cut set here C, which contains a bunch of vertices that you want to cut, and those vertices are connected in some way to here, here, something like that, and those can be connected here too, and something like this. So if you have this situation, then the cut size vertex, to cut it with vertices, your cut size will be the size of C, but you can always kind of emulate this cut by considering this vertex with all of its neighborhood on one side, doing the subgraph complement that will remove all of the edges that are between C and pi2. And then you repeat this process for all of the vertices, and that gives you that you can disconnect like you can basically emulate the same cut you were doing with vertex cut with subgraph complement cut. And so we show that we can do we can do as good as vertex cut, but we are not limited to doing this. So like there's some diagram that you can show that have really good subgraph complement cut. For example, if your diagram looks like a clique, well, a clique would need like a lot of vertex cut to do the whole to split it in half. Actually, you need to cut every single vertex, but subgraph complements you can always do it in just one shot, which is really neat. And so okay, even if you have this kind of lemma, which is cool, that doesn't really give you a way to find good subgraph complement cuts into your diagram, and there is no analog of like sparsest cut but subgraph complement version, for two reasons. First, people don't really care that much about that problem, I guess, and the second reason is that like it doesn't have the same kind of structure as sparsest cut, vertex version, or edge version, because those kind of problems, they look at region where there's low connectivity, and they kind of recursively do something where they aggregate the vertices and something like that. And but those kind of recursive ideas don't really work with subgraph complements, because sometimes with subgraph complements, you want to add a bunch of edges because you want to complete a clique, and then you want to remove the clique. So you don't have that recursive nature, which makes like everything kind of breaks down. However, me and Thomas Lakunen were working on this, and we found out that you can still do something nice. So what we found is that there's a way to take if you use an algorithm that gives you a good vertex cut, you can extract the optimal subgraph complement cut out of that vertex cut, which is kind of a proxy. Like you use the vertex cut to give you some kind of a good cut already, and then you improve it by just doing subgraph complement. And I guess I can show quickly the idea behind this. So the idea is to consider, so you have like exactly as above, you have your cut set and pi2 that you want to split. So we just put here C and pi2. And basically you want to remove everything that is here. But you don't, so what you can do is just consider the bipartite and do subgraph. So just consider all of the vertices that actually play a role in this, that have an edge. And once you consider that bipartite graph, you can look at the biagency matrix. So here we'll have like C1, C2, CK, and I'll say like P1 all the way to Pn. and this is the bi-adjacency matrix of your graph, then what you're really doing is every time you're adding a subgraph complement to this, well, since we don't really care about the edges that are in between C and in between pi2, it's kind of just saying that we're adding a B-clique into that bi-adjacency matrix or bipartite graph. So a B-clique, how it looks like if whatever, like you choose, okay, I want to take C1 and let's say C5 and P1 and P3, and then it's just the matrix that has like a 1 at those places and 0 everywhere else. So you can take those, and a matrix written like this can be always written as like an outer product of the set of vertices A and B that you're considering, where A is a set on C1 and on C, and B is a set on pi2. So the question you're really solving is M plus mod 2 some sum over I equal 1 to R of AI BI. You want this to be equal to 0. So you're adding a bunch of B-cliques until everything is just 0. And if you use the fact that everything here is mod 2, this is equal to the same I equal 1 to R AI BI. And if you're like familiar of seeing some like general linear algebra algorithm in the direct notation, this thing is exactly the rank factorization of a matrix. So the minimal R you can do here is exactly the rank of your matrix. And more than that, the rank factorization algorithm gives you, like, you can go and read out the lines of the rank factorization, and that will give you what kind of vertex set you need to use to actually perform those kind of cuts, which is kind of interesting. Like, it turns out that it works really nicely. So that's cool. So whenever you have those kind of low connectivity in your graph, you can use those kind of techniques, and you have like really good subgraph complements that you can do. So that works really nicely. Another thing you can do with those kind of ideas is kind of related, but a bit needs some, I guess, a separate section. So one thing that we've been exploring nowadays is, instead of just considering doing stabilizer decomposition all the way down on the diagram, we might want to consider doing some stabilizer decomposition for a bit, and then once we arrive at some point, we want to take the ZX diagram we have and throw it into something like Cotangra or like a general tensor contraction algorithm, and just see how it goes. And the reason why you want to do something like this is that Cotangra and those kind of contraction algorithms, they scale exponentially with the tree width of your graph, which is kind of a weird graph theoretic measure. But stabilizer, they don't really care about T gates whatsoever. They just like consider tensors. And on the opposite, the stabilizer decomposition, they only really care about T gates, and they don't care about everything else about the graph. So both problems are kind of hard, but not hard for the same reason. And so you can try to like make the problem easier for Cotangra by using the fact that like you can kind of attack the hard part of a diagram with stabilizer decomposition. For example, if you take a diagram that, okay, how can I say it? Yeah, okay. For example, if you have Cotangra or something like this, I mean, well, okay, Cotangra. Cotangra really doesn't like stuff that have high tree width, and tree width is always lower bounded by the size of the maximum clique in your tensor network. So maximum clique, max clique. So the max clique is really what you want to lower. Well, what you can do is you can take your ZX diagram that looks however, and you can look for the max clique in your ZX diagram. Like, for example, here, I guess my max clique would be, I just made it happen. So this is the max clique. right? Yeah, this is a clique. So this is your max clique. And what you can do is, oh, well, I have a subgraph complementation operation that just says I can reverse, like I can flip all the edges, so I can basically remove it, the whole clique for the cost of 2 terms. And so you can go around with like killing the cliques and then throwing that to Codsi, and that helps. And we've been trying to do those kind of things, and like I think we haven't found a single instance where that actually hurt. Like it just works all the time, but better than just taking a simplified ZX diagram and throw it to Codsi. We take the ZX diagram, we do this kind of sparsification trick, and then we throw it back to Codsi, and we save like orders of magnitudes, like depending on the diagram, you can save like 10-fold or like 400-fold depending on the diagram, and that works really nicely. I guess the only caveat I need to mention, it's like in general, it's not that great to simplify a diagram before showing it to something like Codsi, because the tensor network gets like a lot denser, and Codsi doesn't really like this. So it's not always faster than just like sometime, I guess, the path of circuit. When you take a circuit, you can do 3 things. You can just throw it to Codsi. You can simplify it. Simplify. I'll just put simp. And then you can throw it to Codsi, or you can then sparsify it. Sparsify. And then throw it to Codsi. And from our testing, this path here is always worse than this path here. So we can always do better than actually just simplifying better and throw it to Codsi. However, it happens that a lot of the time, just throwing it to Codsi helps, is faster than using any ZX simplification whatsoever. But from time to time, it is better to sparsify and throw it to Codsi. And you can kind of check that in advance, because Codsi can give you like the cost of contraction. So it gives you kind of a cool pre-processing step, and like, oh, would it be actually better to incorporate some stabilizer decomposition to make my contraction algorithm more efficient? And those kind of ideas we've been working on these days, and like we have some more ideas to improve upon this, and we think we can make, like, I guess, bigger class of circuit more efficient by doing like this path here. And we were kind of working really on that path, on like kind of a hybrid method between stabilizer decomposition and like general tensor contraction methods. And yeah, I think that was most of what I had to say for you today. Thank you for listening.
Okay, thank you very much. Let's all give Julien a round of applause. So now let's open it up for some questions. So if anyone has any questions, then you can either raise your hand in the chat thing, or just open your mic and fire away.
Yeah, Julien, maybe I missed it. Like, what are the next steps?
Okay, the next step is actually like we're considering how. So first, there's something you mentioned to me that was kind of cool, that you don't actually need to do the subgraph complement while cutting. You can just kind of extract the cliques in some way. So that's something we want to look at. And the other thing we really want to work on at the moment is the way we transform a ZX diagram into a tensor network for Codsi, because you cannot just consider your spiders as tensors and throw it to Codsi, because those are really, really high degree tensors. So like the dimension is really like, it's way too big, and you cannot like make it consider the rank of the tensor all that much. So it's not that great. So the way it's implemented at the moment in physics is that edges are tensors and vertices are hyperindices. And that works okay, but it's not great. So one thing we've been looking at the moment is kind of transforming the tensors. Like when you have like a highly connected spider, you can do like this kind of MPS decomposition where you decompose it into like something like this. And then all of your tensors are small, but then there's a question about the ordering you want to put your spider in and like what are the edge. So you might want, let's say, to add some like an edge here to give some Catengra some freedom on how you want to contract, or not maybe just a loop, but maybe do something like this or something along those lines to make it go faster. And like if you do this, then you can always like somehow the graph theoretic things you've been trying to optimize, they translate better to actually the tensor network that Catengra actually receives. And the other thing is the thing we talked about, that like you can do subgraph complement, but I guess I can go back to the definition. Yes, here you can do this whole step, but you can there's no like somehow you can just stop here and take that as your tensor network. I mean this not necessarily was it? Yeah, you can do the pivoting happen, and then you'll not really stop here, but you can do the pivot here by adding like a pi, like an angle here. And so you don't really necessarily have to cut, but then you have like an unsimplified ZX diagram, but that's okay. You can still throw it to Catengra. So there's kind of tricks you can do here to minimize the exponential growth of the stabilizer decomposition by doing those kind of tricks. So you can attack more cliques in your diagram before throwing it to Catengra.
Right, you're saying that you can sparsify it without having to introduce additional terms. So that's like a cheap way to do that. But the other thing you mentioned about like doing the MPS thing with the spiders, I would be surprised if that works well with Catengra, because Catengra like is using the smarts of these hyper indices to do this kind of stuff for you, right? Like it's sort of figuring out, oh, in which order should I contract given this is a hyper index, so that I have this freedom to decompose this hyper index in whatever way I want.
Yeah,
so in principle, it is finding something like that, like for you.
In principle, but to be fair, Catengra is not all that mighty. Like sometimes it doesn't even found contraction order that are better than just like state vectors. So I guess that's true, but also just yeah, I guess that's true, but like also the fact that just taking a ZX or like a circuit, simplifying with ZX and throwing it into Catengra makes it slower, meaning that Catengra is doing something kind of sketchy about those hyper indices, because like in principle that tensor network is just way simpler, but like it doesn't really find that it's simpler just because, like, for example, the 3 width is high or something like that. So this kind of gives him like the freedom to find better contraction path.
In practice, I think this is because hyperindices mean that the heuristics Catengra is using, which is based on tree decomposition, has to look at it's like a hypergraph, not a graph, that is trying to find tree decompositions of, and that makes all the heuristics a lot worse, basically, because everything becomes much denser. So it's much better if you can stick with the graph rather than a hypergraph.
Thanks.
So I have a question. I have a fairly naive understanding of simulation techniques. So I know that if you have some kind of circuit which is somehow planar, then you can simulate this. I'm not sure if it's in polytime, but it's pretty efficient. So in this, there's a lot of talk about the kind of the sparsity of your graphs and breaking them up into doing edge breaking and so on. Does this sort of thing give you an understanding of some class of circuits or some class of ZX diagrams other than the obvious ones, which are the extremely sparse ones, which are efficient to simulate?
Yeah, you get the same understanding, because basically it's the same kind of argument that they use for those kind of planar things, is that you have some class of graph that have like separators theorem. So they like, you know, that there exists like a small cut that cut the graph in two. For example, if you have a planar graph with n vertices, you know that you can always split the graph in two by using only square root of n vertices. And that's really kind of a really good efficient cut. And that's where you can find, like, you can prove that any planar ZX diagram, as long as you don't have more than any planar ZX diagram, you can do cuts like this. And by cutting, you still keep the planarity of the graph, so you can do this recursively. And like the existence, like those kind of graph theoretic theorems give you like some existence of good cuts. It's kind of just a guarantee that the kind of algorithm we've been talking about just works on those kind of graphs. So like in the sense, like the algorithm will find those kind of cuts, but those theorems just guarantee that they exist. And by like just this argument, you see that like a planar circuit, as long as it has less than n squared gate, then you'll have something that do like 2 to the square root of the number of gates algorithm. And as long as it's less than n squared, that's better than exponential. So that's how you can kind of find those like planar argument. And there's also other like separator theorem, like sphere separator theorem, and like more exotic kind of graph where you can do those kind of arguments.
Right. So it's not just that the graph that you start off with has to have a low Cheeger constant, if you like, but also that it has to have a sort of recursively low one.
Yeah.
Each time
for those kind of argument to work all the way down, such as planar, you need to be able to say, okay, once I've cut my diagram, I'll be able to do those kind of cut again, and those kind of property, you get it with planarity and some stuff like that. But like, I guess in general, if you're just looking for good cuts and you don't have any guarantee on your diagram, you can just throw a dedicated algorithm to find good cuts. And if you had a planar graph, like you're guaranteed that this will find something, but if not, like it will look and it might find something.
Okay, thanks. Yeah. I guess then that the thing about planarity might generalize to if the graph has some kind of topological embedding onto like a manifold or something, in which case your connectivity is always like locally restricted.
If I remember correctly, if you have a graph like a circuit that fits into I think it's 2 to the number, like if you do it recursively, it's 2 to the number of gates times the number of folds in your embedding, like a number of folds. So as long as if your graph fits on the torus, then you can just make this argument all the way through. But if you start with like a really it embeds in like a really high degree, like a lot of holes, then maybe by cutting now you can embed it in less holes and stuff like that. So it works nicely because of planar, because planarity we have like this nice analog of like what's a planar diagram. Well, it's just a nearest neighbor circuit at the end of the day. But for other kind of topology, you can make it work, but it just doesn't have that nice intuition of like what it looks like for a circuit to fit on a torus or something like that. But like this exact same argument works.
Cool, thanks. I wonder then whether, so I was thinking that in quantum error correction, we're quite often thinking about codes which are embedded on some kind of manifold. And actually the opposite is true in these, where for those kinds of things, you normally actually want the Cheeger constants to be very high, because this gives you better kind of properties for error correction and so on. But for those that are defined on manifolds, in those cases, you will literally have a well, maybe that's not true. I was going to say that you'd have a circuit which can be embedded on a manifold, but I guess actually the circuit would be operating in the kind of perpendicularly to the surface of the manifold. So maybe and that doesn't make sense.
One thing I've been thinking about is how to embed circuit into a manifold with like a low number of holes. And they're kind of good tricks. Like one trick I found is that you can always embed any circuit. Normally a circuit will take like a manifold with n squared hole, but you can always embed it in like n log n hole. It's like n log n hole. And you can do this and the cost of doing this thing is the circuit gets logs times deeper. And the kind of idea to make this happen is that you can take your circuit and you can kind of build like some bridges between some wires. And actually what you can do is you can build a skip list as a data structure on top, like a skip list of bridges. And if you analyze it, like how a skip list actually works, it makes it that like you can get that n log n kind of holes, and the depth is just log n because it's the depth of a skip list. So you can do those kind of things, but in general they don't work. Like they like clearly don't give you something that works in general, because it would give you some advantages. But for low depth circuit, that could work. It's kind of interesting. But like here, like the number of holes still depends on the number of qubits, so it's not that great, because here like this kind of breaks down to like n log n times the number of gates, but there's kind of tricks you can do. So
Cool, thank you very much. Does anybody else have any questions? Okay, I'm going to take that silence to mean no. In which case, let's thank our speaker again. And so next week there is a strike, and so we will a UCU strike, and so we will not be having a seminar kind of in solidarity with that. But the week after, I'm looking for a speaker. So if anybody would like to talk on the 27th, I believe it is, then please let me know. Okay, thanks everyone.
yeah, thanks.